4 o'clock Eastern this afternoon. I think this was bad news.
Will we get the reasons for this?
You know what I know. How can there be a reason? So I want to talk about some science and a little philosophy as well. And this is, I should say, work with my student Taryn Hall. So using the Y chromosome is a nice form of evidence, and it's a little complicated in that all the components of the profile are not independent. As a consequence, the numbers are not as extreme as we see for autosomal profiles, and that might make it a little easier to wrestle with some of the ideas. We're not seeing 10 to the power of 50, we're seeing 10 to the power of 5. A little easier. I want to talk about entropy, which is a nice way of addressing dependencies. I want to talk about the likelihood ratio and a couple of comments, and I'll concentrate on 3 different ways of presenting the evidence in court. The counting method, so-called kappa method by Charles Brenner recently, and the theta correction that I've been advocating. I will not talk about some nice work by Mikkel Andersen on discrete Laplace methods. So I'm going to talk about matching probabilities leading to likelihood ratios. The counting method's a purely statistical one, not a very satisfactory approach. The method that Brenner published, dating back to work by Turing, uses the proportion of singletons in a database, has some nice properties. It's not a genetic model, unlike the last one I'll talk about, which puts the biology into the interpretation. I'm going to be referring to a nice published database of this version had, I think, 19,000 Y haplotypes in the database from several different populations. It's publicly available. I think it's reliable data. It's been carefully QC'd. When you look at the data set, just amalgamating over all the populations, we can count how many times a haplotype appears. Most of the time they are singletons. Most profiles occur only once in the database, but there are as many as 11 matching profiles in this database, almost certainly 11 men fairly closely related because they match at 23 loci. So the first problem is that we've got 23 genotypes, 23 alleles, these YSTRs. We can't multiply them together because of the lack of recombination. A man receives a Y chromosome and passes it on intact to his sons, which of course makes the loci dependent, except that mutation occurs, as far as we know, independently among loci, so that the lack of recombination to some extent is countered by the independence of mutation. There's a lot of talk in the forensic literature about linkage disequilibrium. It's not really appropriate in this context because that concept almost always refers to just 2 loci. When we look at the LD, the traditional 2 locus LD values for Y chromosome data, most of the pairs of loci are in linkage equilibrium. There's been a nice couple of papers in the last year or two about using entropy to try and address the issue of dependence across multiple loci. So entropy is just this little sum of the variant frequencies times their logarithms, add up over all the types. So if there's a locus with only one allele, no variation, the entropy is 1. If there's a locus with multiple alleles, all equally frequent, the entropy is log of that number. So entropy is some measure of diversity. We would like it to be high for forensic markers. If we've got 2 loci, then their joint entropy, the entropy of the 2 locus haplotypes, is just the sum of the single locus entropies. One of the interesting questions is how many YSTR markers do we need? Do we need 23? Could we get away with a smaller number? So what's the consequence if we've already got a dozen or so markers typed? what's the value, the added value in bringing in another locus? So we can address this by asking the question, how much more information does this additional locus have? So the entropy of the new locus conditioned on the previous haplotype, the previous markers, is just the difference of the joint entropy and the marginal of the haplotype, suggests that we might build, this is not my idea, it's from those papers I referred to, we might build up the profile by choosing to add markers which are most independent, have the least dependence on the previous markers. So looking at the YHRD data, here are some loci, here are their single locus entropies, and we're showing them in the order of adding them to a profile, ordered in such a way that we always choose the maximum conditional entropy. So it's sort of an interesting point that the order of building up the overall diversity is not the order of the single locus entropies. Sort of a counterintuitive thing. It just reflects this complex dependency pattern among the loci, reflecting mainly mutation that determines the pattern. So consequently, these orders will be different in different populations, different histories. So anyway, the point was here that after a dozen or so loci, you don't get much change in the forensic value of the profile. There'll be some, but not a great deal. The entropy decreases with the mutation rate. The more so the more mutation, the more alleles there are, and the more information, and so the entropy will go up. This is the YHRD database. So I've got this pet peeve about random match probability. I would like to talk about profile probabilities, the chance of drawing a person from a population with a profile. Not a particularly interesting quantity. It's not much point saying this has a low probability. All forensic profiles are rare. Most forensic profiles don't exist. Most possible ones don't. What is of interest is what's the chance of matching? What's the chance of seeing the profile if we've already seen it once? This is the forensically relevant quantity, and it's not going to happen, obviously, but it would be nice if we reserved the word match probability to instances where we have matching, the comparison of two profiles. It's the match probability, of course, which features into the likelihood ratio. The match on the one hypothesis versus the match under the other.
Excuse me, in this case, A must be different A, because otherwise the probability is 1.
Yes.
Instead of A given A is 1.
Yes, it's a bit of shorthand notation.
The chance of seeing the profile in a random person given that we've already seen it from another person.
Another index, sorry.
So it's not in the notation, but it's explained.
Well, it's chance that this person has A, given that we already have A. It's the same A.
Yeah. I agree.
We understood what you meant.
A little diversion on what we've been hearing about the prosecutor's fallacy. It's rather disturbing how little progress we've made, I think, since Bill Thompson's paper. I'm a member of this very large enterprise called OSAC in the US, set up by the Department of Justice to try and address the scientific underpinnings of forensics. Last week I heard some very distinguished forensic scientists saying that if they see a match based on their expertise and their experience, they're quite comfortable in telling the court that they've got the right person. It's not limited to forensic scientists. There are many people in this OSAC who say, well, maybe we should allow the transposed conditional. If with some caveats, if the expert accompanies such a statement with a data-driven statement about the accuracy of examiners who draw these conclusions. I think this is very disturbing. I can't see any circumstances where we would present the evidence around the wrong way. The only case that I'm aware of in the US where the prosecutor's fallacy went further than the trial court and resulted in an initial overturning of the conviction was, I think, was Nevada versus Brown. It went to the Supreme Court. The Supreme Court upheld the conviction. They said that the forensic science expert, and I think Bill was part of an amicus brief, their report provided no warrant for excluding the DNA evidence because the report did not contest that the DNA evidence matched. The DNA evidence remains powerful inculpatory evidence, even though the prosecutor's fallacy was committed. So it doesn't matter. We've got a match, it's strong evidence, and who cares about this other little bit at the back of the equation about the prize? So there was an opportunity that we lost in the US. So what can we do? The usual way is to get an evidentiary profile and see if we've seen it before. Look in a database. If we've seen it this number of times in a database of that size, then an unbiased estimate of the population proportion is just the ratio, the sample frequency. We're going to run out of data. We've already run out of data a long time ago. If we've got L loci, we're going to at least 10 to the power of L different possible profiles. So most of the time we don't see the profile in the database. We might say, well, if we don't see it, we could at least put a confidence upper bound on the population proportion, and the 95% limit's approximately 3 over the sample size. The problem with this approach is that we'll get the same answer no matter how strong the evidence is. We might find the 7 locus profiles not in the database, and if those 7 loci don't occur, those 7 alleles don't occur together, then a 17 locus profile won't occur either. This is Charles Brander's point. Changing the simple proportion by adding the profile once or twice is not changing that situation, and it's still not giving us a match probability. So I don't think this is a very useful way of proceeding. The Kappa method is a nice way of approaching problem, and it seems to work fairly well. It takes us away from worrying about the details of the profile. So the answer doesn't depend on the particular alleles. The answer depends only on how many times does this profile occur in a database. And Charles was interested in the usual case where the profile doesn't occur. So he adds it to the database, an augmented database of size n, and then kappa is the proportion of profiles in that augmented database that occur once. 1 minus kappa over n is an estimate of the match probability. Charles uses the word popularity. If in fact the profile occurs p times in the augmented database, we would modify the match probability to p times that, although he says this may not be a good idea. He was focusing mainly on the situation where the profile had not been seen previously. I've done some simulations, and this is the frequency in a population from which I drew a sample. Here's what Brenner would tell me I would expect to find in the population, and we get some scatter around the equality line until I put migration between the populations I simulated. The databases we use are composite in the sense they come from multiple subpopulations. Our databases are not homogeneous, so there's always some substructure in the population represented by the database. And when we allow for migration causing these dependencies amongst the subgroups, then we find that the kappa method tends not to be conservative. I looked at the consequences of the profile having been seen before. This is the case that Brenner looked at. So it's a nice, and I've changed the simulation parameters, so it's a lot smaller probabilities there. There's a nice tight cluster of the actual value and the Brenner estimate for previously unseen profiles. If the profile has been seen previously, then the estimates become less reliable, as Brenner acknowledged. Looking at the YHRD database, just regarding as a single entity, 19,000 databases, the counting method would give some number of these orders, depending on how we approached it. The kappa method would give something substantially smaller than the simple proportion. So this has the danger of understating the strength of the evidence. This is a little closer, although there's no biology, there's no genetics here. And I think once again, this kappa method will give the same answer no matter how many loci are involved. So there is a genetic approach which has been used previously for the autosomal loci. If we draw two profiles from a subpopulation I've just labelled of I, then the chance of getting two copies, more or less, is the square of the frequency in that population. We're addressing if we knew these proportions would be fine. If we had the subpopulation identified and sampled, and we had a good estimate of this, everything would be simple. We don't know the subpopulation that's relevant in practice, so we don't have these numbers to square. We need to take expectations over evolutionary replicates of this process. And that brings in this genetic parameter, which in the forensic literature has been called theta or FST. It's population specific, and it depends on the expected profile probability, the expectation over all replicates of the process. So the match probability in essence, has this theta as a default minimum. The profile probability might be exceedingly small, but we still have this, if you like, it's the old ceiling principle. It's the lower bound on the match probability. We can average that over all subpopulations and over all profiles, and we get a theta or an F. This is the conventional FST value. There's a lot of theory in population genetics telling us how big these quantities should be, and under a single stepwise mutation model, they're given by this little equation, the population size and the mutation rate for the haplotype. And if the loci had the same mutation rates and they were mutating independently, then the log of theta is proportional to the number of loci. So as you get more and more loci, the theta changes, it gets smaller, the strength of the evidence gets stronger. And that will continue. And this suggests that we should just keep on adding loci forever. We'll get stronger and stronger evidence. We don't see that in practice. Here's some simulations for populations evolving under the stepwise mutation model. The number of loci minus log theta, and they are indeed increasing, but this is the predicted linear increase on the log scale. In fact, things tend to tend off after a while. If these thetas are measuring identity by descent, if we've got two profiles identical by descent at 20 or 30 loci, we've got the same male lineage, we're going to continue getting identity. We've looked at estimating this quantity theta from data, and the simplest estimate is gotten by comparing the matching proportion for haplotypes within populations versus that between. And so here are the individual Y haplotype loci put in an order. So this is just using that locus. Down here we're using all the previous loci. Here are the matching proportions for two haplotypes taken randomly from the YHRD database at one locus down to 23 loci. The matching proportion goes down, of course. The matching proportion between populations is going down also. It's smaller, but not hugely smaller than the matching within. And here's the theta estimate. So they're going down nicely, as we would expect. And As the number of loci increases, we've only got 23 loci to play with here in this data set, so we've only got one estimate, and here it is. If we look at 10 loci, there are lots of ways of choosing 10 sets of loci instead of 23. There's a huge variation in the estimated theta value. So these quantities, they are very dependent on the loci we look at, because the mutation rates are in fact different at these loci. Putting in, now there's a logical problem here. These thetas are meant to describe the, if you like, the dependencies amongst the subpopulations. The only way to estimate the theta is to have data from those subpopulations. If we had the subpopulations identified and sampled, we wouldn't need the theta anyway. So we have a single database. We're going to have to assign a value of theta on some rational grounds. And it's not possible to estimate the theta that we want from a single database. We can estimate the theta that will apply on average to any of the subpopulations, assuming a large number of subpopulations. So here's our within subpopulation estimate, and if we take that as our lower bound on the match probability, it's in fact a little higher than some of these counting estimates and from the kappa method. This is but this applies to the small subpopulations, whereas these apply to the whole population. Here are the range of values for the YHRD5 continental ancestries. They range over reasonably wide range. I think that's all I needed to say. So I would say we have to express the strength of the evidence in a likelihood ratio, expressing the answer as the probability of the evidence under alternative hypotheses, not the transpose. I think we should give an answer that reflects the underlying biology. These are genetic profiles. They come to us with a history that reflects population structure, mutation, migration, all those things. And we've got, I think, a good body of theory which gives us a reliable way to put all that biology into our estimations. That's it. David.
Well, I think it's a good approach. That it's going to be the usual thing about the issues of the sort of subpopulations relevant to a particular crime. It's a bit like the issue we discussed with the bullets on Monday. That I just remember one particular case I'm involved with where the suspect, the victim and the suspect were both Turkish, and she said he spoke in Turkish and that they were from a particular remote region within Turkey, and the sort of relevant subpopulations are very different. And so, I mean, you sort of said that, but you don't have much idea how to estimate the quantities there, and any estimate in a large database are probably going to be too small.
We don't have estimates relevant for a particular crime.
Yeah.
We have to.
But even an idea of what it might be like in a very isolated subpopulation.
Oh, I think we have worldwide survey. I think we've got a good understanding for the likely range of values. We have done that.
But there aren't many databases that have the sort of very localized geographic information. You might have it at national or perhaps state level.
Sure.
Is that growing all the time that way?
Excuse me?
It's growing. They keep adding.
Oh, the databases are growing. Not of course, quickly enough to avoid these problems. Okay.
Also, localization, I think, depends upon where the person whose DNA you sampled happened to be at that time. They may have lived there all their life. They may be...
Well, we're not interested in that person. It's the other person we're interested in.
Sure, whoever it is.
I think one of just to that joke.
I just wanted to mention something about what you started with, because I had the good fortune of hearing a talk and reading Eric Landon, who was the head now of the President's Council of Advisors.
Co-chair.
And
No, we don't hear you, Johnny.
sorry. I had the good fortune this last year to a meeting and going to a special talk of Eric Lander, who was the head of the council, President's Council. And one thing, he's an awfully smart fellow, of course, but more importantly, he told us that the issues they address come from the president. The president asked him to look into it. So it's kind of interesting that President Obama got interested in the accuracy of forensic evidence. So it'd be
I
very
doubt the
interesting.
president is opposed to multiple contributed DNA profiles.
Well, I'm not saying, no. He asked them to look into it.
Yeah, he might have been advised and got worried. But,
No, I'm saying he asked them to look at it. I'm just saying, I don't know what he believes in. But it'll be very interesting to see what support they give for their findings. That's all.
Can we just have one more?
Yeah.
Oh, I'm so sorry.
Oh, yes. So it's a bit technical, my remark. With the student, Julia Chireda, we also looked at the Brenner method and tried to understand the arguments. And actually, they are very difficult to understand, and perhaps they're not even correct. At some point, he's making an approximation which he tries to justify on actual biological grounds. So I just wanted to point out, you can replace the approximation by another estimation, and we have alternative to kappa. We're using also the pairs, because for the defense is saying 2 times we saw a different person with the same new haplotype, and the database gives us information about how often that happens.
Yes.
And it led to something which is almost the same as what the kappa method delivers. It has some more uncertainty in it because we are using a part of the data which is more variable, but I think it is more argued.
Yeah. So I think the simulation showed that looking at the doubletons as well helps. But it has more of a, I'll follow up on that.
Yeah.